Okay, so last time we were talking about this example and some related thoughts. And the big idea, I won't go through the details again, the big idea is if you want to understand something about a line, if you want to draw certain kinds of geometric conclusions, and of course what we're going to do is we're going to first represent this with some algebra, and then we're going to do some calculus to that algebra, right? But the question is, how do you interpret what the calculus says? Right, so the main way, the first step in that process is to figure out, well, wait a minute, what kind of algebra did you use? Are you applying calculus to the function whose graph is that line? Or, totally different, are you applying calculus to the function for which one of the level sets is that line? These are really different functions, right? And if you apply I'll say the right calculus to the wrong function, right, you're going to get garbage nonsense results. Right? So it's very, very important to be able to make the distinction given a geometric object, which, I mean, there's nothing wrong with either one of these functions. They both relate to this line, but in specific and different ways. Right? So it's very, very critical to be able to know what the connection is so that you can know what kind of calculus to apply to it. Okay, so again, we talked about that last time, likewise with parameterizations, of course. So here is a slick move, I'll call it. This is a wonderful little tool for your toolbox, and that is to make the observation that not only is every graph a level set, but we have a simple prescription for how to turn a graph into a level set. And this works every time. And it's pretty fantastic. So it goes like this. I mean, frankly, here's the algebra. The algebra here is practically nothing, right? You can see that this is not only converts the graph algebra into level set algebra, right? But furthermore, this is a reversible operation. So it's not just that the top equation implies the bottom. It's that they're equivalent to each other. Right? So in other words, nothing actually happened here in terms of what does this algebra represent. But notice the first, right, is viewing this as being a graph. And the second down here is viewing this as being a level set. So I've successfully turned a graph into a level set. Now, very importantly, related note, the function whose graph we're looking at and the function one of whose level sets we're looking at are very different functions, right? It's kind of like in this example we were just looking at. These two functions are really different functions, right? And so it's critical to be unambiguously explicit as to exactly what function are we talking about, right? So here you go. Here's the this first function, the function whose graph we're looking at is called f. It has n input variables and it has one output variable. Okay? There it is. Right? By contrast, the function here, one of whose level sets we're looking at, in other words, the thing that's being set equal to a constant here, that's a very different function. First thing I'll point out about this function that I have circled in kind of the dark blue here, it's not f. It's really importantly not f. Right? It's a different function that has, again, that formula. And what are we going to call it? Well, we can't call it f. It's definitely not f. So I'm going to call it g. And furthermore, it's structurally very different from f. F is a function of merely n variables, x1 through xn. This expression here is more than that. This expression does depend on x1 through xn, but it also depends on y. Right? Y is now an input variable for this function called g. Right, so now again, the algebra here, don't be fooled by the triviality of this algebra of taking what's on one side of the equation and tossing it over onto the other side with a minus sign. That's trivial. That's not the point of what's happening here. The point is being able to make a proper interpretation what is a graph, what is a level set, which functions specifically are we looking at graphs and or level sets of, and then choosing accordingly. Okay, so now why would we ever care about such a thing? What's the point? What have we gained by doing this? Well, again, we know, we're going to know, we don't yet, but we will soon know some calculus of graphs. And not long after that, we will learn some calculus of level sets. And the reality of the situation is that they tell us different things. It's probably not too surprising. But there are some conclusions that you can get from the calculus of level sets that you can't really very conveniently get from the calculus of graphs. So if you find yourself looking at a graph, some function f, and you're like, golly, I really wish I could apply the calculus of level sets here, because the calculus of level sets would just take me right to exactly what I want. Wouldn't that be nice? But too bad, I'm not looking at a level set. This is the little fast one that you can pull. That will make you, yes, in fact, now at this point, you are looking at the calculus of level sets. And this tells you exactly what function one of the level sets it is that you're looking at. So here's an example, just to get some dirt under our fingernails. Suppose you find yourself looking at the graph of this function right here. All right, so just first a quick recognition. Doff with a cap to, yes, indeed, this equation is the graph of that function f. And again, calculus of level sets might be exactly what we need, right? Maybe what we need is a vector that plays a certain role with respect to this surface. Okay, if so, if you need the calculus of level sets, well, definitely don't use this function. That's not the function for which we're looking at a level set. We're looking at a graph of that function. Right? So what you have to do is you do the little algebraic triviality, little algebraic equivalence. Nothing happened there. These are morally equivalent equations. Right? But now I can say, hey, look at this. I have myself a level set. And so I can apply the calculus of level sets to this function, and whatever I conclude from the calculus of level sets of this new function, again, critically, not f, will tell me what it is that I wanted to know about this original surface. And again, originally it came to me as a graph. I chose to view it as a level set of a different function. So it's a really nice move, very slick, very powerful. Tragically, it is a one-way move. Every graph is a level set, but not every level set is a graph. And here's an easy counterexample. See if I can get that. Okay, there we go. Yeah, here's a level set. All right, we're looking at a level set here of that function, g. Right? That level set, this equation, in other words, this equation we easily recognize. That's the equation of a circle. There you go. That's the level set. Can I reinterpret this level set as being a graph? Can't. There's a couple different ways to say it, but I cannot rewrite that equation equivalently as y equals a function of x. You just can't do it. Now you can narrow it down to a couple of possibilities. You can say, well, y is going to equal to either plus or minus. I don't know which one, right? But again, you haven't solved for y as a function of the other. Function means one output from any given input. So, dead in the water. If I would like to be able to use the calculus of graphs as applied to help me understand this curve, I've got a problem. Right? It's not a graph, so how am I going to use the calculus of graphs? Okay, more on that later. There is more to say about this. There is a clever workaround, but that's for a later date. Okay, let's talk about rotations. This is another one of these little, what I like to call little freebies. we talked about before, certain algebraic observations you can make at a glance, and you get these instantaneous, awesome conclusions. So the first one that we saw is looking at equations of planes. If the equation of the plane doesn't have any y's in it, right? Easily observed, casual glance. If it doesn't have any y's in it, then it's parallel to the y-axis, right? Powerful geometric conclusion, effortless to notice. So here's another one. If you have an equation of three variables, and if that equation, let's see here, let me do it like this. If that equation involves x's and y's only as part of this expression right here, this is a very important, specific, critical expression. If x and y only show up as in terms of square root of x squared plus y squared, no other x's or y's anywhere in the, no sine x, over on the side of the equation or something, just only as part of square root of x squared plus y squared. Again, pretty easily observed, and you get this really powerful conclusion. Your surface is rotationally symmetric around the z-axis. And you can think of this a couple of different ways. I find it satisfying myself to realize that if this is the case, then these 2 points achieved, you'll notice, by kind of rotating one into the other around the z-axis. Well, they're totally different points. They have different x coordinates. They have different y coordinates. But x and y don't really kind of, as they are, show up in the equation. They only show up as part of this square root expression. And those 2 points have the same value of that square root expression, because that square root expression is this distance, and these 2 points have the same cylindrical coordinate r because they are rotations of each other. Right? And so, yeah, they have different x and y, but that doesn't affect how the arithmetic of the equation works out. Here's a different way to think about this if you're not satisfied by that point of view. Come on, Zoom. There we go. If this is the case, if x and y appear only as part of this expression, keep in mind, in cylindrical coordinates, this is just r. No thetas. All right, so x's and y's are going to convert into cylindrical algebra with no thetas in it. Okay? Now there's also the z in the equation. What's going to happen when you convert the z into cylindrical coordinates? Well, nothing. It's also a cylindrical coordinate. So again, no thetas show up. And so the punchline is, pretty easily observed, I think, that there are no thetas in such an equation. And we've already made an observation last time, I forget exactly, but some recent lecture, if a cylindrical equation doesn't have thetas in it, so it's rotationally symmetric around the z-axis. Is everybody buying it? Is everybody happy? Okay. So let me show you why I think this is very, very valuable. I think this is huge. Here's the critical example, and that is if a surface has rotational symmetry around the z-axis, then all of the theta slices look exactly the same. And furthermore, you can generate the entire surface by rotating any such cross-section, just rotating it around the z-axis. So, easy algebraic observation. Just look for the x's and y's. Make sure they only show up in the relevant form. And then you get to just magically say, oh, this is rotationally symmetric. And then I'm going to look at a particular convenient cross-section, convenient for my least effort possible. And then I can just say, oh, yeah, just rotate that around, and boom, you got a picture. You know exactly what your surface looks like. Okay, so here's the example. Let's understand this equation. Let me zoom back in here. Let's understand this equation right here. Now, you may quibble and say, I do not see a square root. on that expression, on the x squared plus y squared. But keep in mind, this is equivalent to z equals the square of x squared, square root of x squared plus y squared. So it's again, when I say x and y appear only in the certain form, I don't mean, it's not a point about the typographical, how you chose to write it down. These are equivalent, and in this expression on the right, x and y appear only in the required special form. Everybody okay with that little nuance? Everybody's happy? Okay, so sweet. This x and y appear only in the special form. I instantly, finger snap, know that this surface is rotationally symmetric. That means I can look in any plane containing that z-axis. Pick your favorite plane that contains the z-axis. I like the yz plane, frankly. I like the yz plane, namely where x equals 0. I like that better than the xz plane, because look how I have to draw the xz plane. The xz plane's a little weird to draw. I'm looking at an angle. It's just a little harder to work with. That's not a big deal. All else being equal, I like to use the yz plane. In the yz plane, this is really easy. There's hardly anything going on. In the yz plane, where x is 0, just plug x equals 0 right into there. And in that plane, our cross-section is a parabola, like so. Everybody okay? Because keep in mind, when I say I'm looking at the cross-section in this plane, that means that every point on this surface, if I'm only looking in this one cross-section, also satisfies this equation, so I get to plug in x equals 0 into my initial algebra. So, so a quick observation about rotational symmetry, and I turn an equation of 3 variables that I'm trying to understand into an equation of 2 variables that I already understand, and now I just have to ask, just a little bit of logistics. What happens when you take this and you rotate around the z-axis? And, well, if you rotate this parabola around the z-axis, you're going to get this kind of bowl shape thing, like so. Is everybody good? A little bit of semantics. This is called a paraboloid because it comes from a parabola in the sense that it is a rotation of a parabola. Okay. All right. Powerful conclusion. By the way, entertain yourself with the rhetorical exercise of how would you understand what this looks like without this rotational trick? And there are ways, but it's nowhere near as handy. It's nowhere near as finger-snapping, immediate, clear as this is. Okay, here's another example. How would I make sense out of this surface? Well, again, x and y appear only in the special form. You can see right there, no other x's, no other y's, just the special form. And therefore rotationally symmetric around the z-axis. Therefore, I can pick any plane containing the z-axis. Pick your favorite plane. Doesn't matter. I don't care. Go crazy. I advise, I think it's convenient to always choose a coordinate plane, right? Might as well. This time, just to show that we can do it, I'm going to pick the xz plane. And you see we're looking at it at a weird angle. And then, could be worse. But in that plane, y is equal to 0, which, when you plug into our initial algebra, our algebra becomes this, which is a hyperbola, and I remind y'all that's part of high school algebra prerequisite, for in the prerequisite trail for this course. So make sure you're good with all that stuff. If you're shaky on hyperbolas, there's an internet full of people who want to help you understand that. And of course, you're also welcome to come to my office hours, the other instructors' office hours, the help room hours. But make sure that you're good and reliable with that algebra. So that hyperbola looks like this. And then again, I just make the rotation argument. You rotate around the z-axis because it's rotationally symmetric around the z-axis, and that produces a shape that looks kind of like that. And being as this is a rotation of a hyperbola, again, you could probably guess the name hyperboloid. Okay. Everybody happy so far? Real quick, this actually gets called a hyperboloid of one sheet. There's good reason for that, which you'll see in the next example. Okay. Let's see here. Let me, however, erase all of that. I'll leave that. Okay. Okay, now, what if it's not x and y that fit the special form? What if it's x and z? Or what if it's y and z? Right, something like that. What does that mean? It means morally the same exact thing. Now, the argument that we made back here about cylindrical equations doesn't work because the z-axis is special in cylindrical coordinates, right? So I can't make that argument, but this argument here works totally analogously, and I think it's a nice exercise to think that through, persuade yourself that this an appropriate adaptation of this argument will persuade you of a morally equivalent solution and theorem. And in particular, in this case, looking at this equation, which of course is totally equivalent to this equation, so feel free to look at whichever one's more convenient. Check it out. Y and z appear only in the special form. So, again, thinking through the reasoning, and again, this is an exercise for y'all, because y and z appear only in the special form, this is going to be rotationally symmetric around the x-axis. All right? Now, again, if it's rotationally symmetric, I can pick any cross-section containing my axis and just understand it in that one cross-section and then, rotate around the axis. And the same idea as in our last two examples, just different rotational axis. So again, you have choices. I've chosen here the XY plane. I could have chosen the XZ plane, whatever. If you're a masochist, you could pick an angled plane. I don't advise that, but I guess you could. But that would be weird. It'd be harder to write down. Anyway, easy choice here. The XY plane, where z is equal to 0, which when you plug into there gives you this algebra. Again, very familiar, high school algebra 2 or whatever they call it, and it is this hyperbola. And so again, we find ourselves in this situation where, well, we know a cross-section, and we know it's rotationally symmetric, so I'll just rotate this blue curve, rotate it around the x-axis, and rotating around the x-axis results in, well, this one's really hard to draw. So I've taken my best crack at it here. What I see when I look at this is two contact lenses that are kind of staring right at each other. I don't know. That's just what I see. But they're kind of two bowls, right? Whose undersides are sort of facing each other. Whatever your favorite metaphor is. But anyway, this too, you'll notice, is a rotation of a hyperbola. So this too is called a hyperboloid, and we have to specify why. Why do we call one? Why do we have to include this clarification of hyperboloid of how many sheets? And that is because these are two different surfaces. They're very different kinds of surfaces. Right? So if we are dealing with two very different looking surfaces, we can't give them both the same name. So the word hyperboloid just doesn't cut it. So that's why we clarify hyperboloid of one sheet versus hyperboloid of two sheets. Yeah. Seem like a reasonable choice? Okay. All right. Now here's some more algebraic tools for equations of three variables. I'm just going to argue by example. Oh, yeah, sorry.
Yeah, I just want to ask why you chose to rotate it about the x-axis.
Well, I didn't choose. That was the only option on the table, because if you look at this equation, right, the only pair of variables that shows up only exactly in the special form is the pair y and z. Right? If I were to try to make a rotational symmetry argument about the z-axis, I would have to ask, do x and y appear only in the special form? And no, they don't. X squared minus y squared is not only a function of x squared plus y squared. Does that make sense? It's just a totally different expression. Okay, yeah. All right. Okay, yeah, so this requirement is critical, this business about it has to be only specifically a function of this expression right here. That structure is critical. Because that expression is what represents this distance, and the whole geometric connection is that when you rotate, that distance doesn't change. Right? So it is very, very, this is a delicate theorem that we're using here. It's very specifically only that expression. Okay. Let's see here. Okay, different trick. And again, I'm going to argue by example. Suppose you have yourself an equation. Here's one. There's an equation, and I understand what that equation looks like. It's a sphere. Easy argument, distance from the origin. Spherical coordinates, if you prefer, whatever. That's a sphere. What happens if everywhere I see a z in this equation, if I just kind of erase and put in its place instead 2z? So specifically, like I've done here, this z, everywhere I see the z, I have replaced it now with 2z. Like so. So my question is, algebraically, well, then this turns into that. Who cares? This is made-up algebraic nonsense. Why am I entertaining made-up algebraic nonsense? And the reason why is what we're going to see momentarily is that there is a relationship, a geometric relationship between the blue surface that I already understand and this green surface that I don't understand yet, but which I might very well want to, and which might be a harder thing to understand at a glance because it's not the same algebra and I might not get correspondingly lucky. So for example, I got really lucky on this one. Rho, spherical rho, staring me right in the face. That makes this easy to understand. I don't have that convenience here with this algebra, right? So, okay, so what does this surface look like? Said differently, what happens? What deformation happens to the surface when I do this algebraic move of everywhere I see a z, I erase it and I put a 2z? And I argue as follows. Let me get rid of the mess. This is, again, I'm not going to prove this. I just want to be persuasive here. This point, 3, 4, 12, that you can check for yourselves, satisfies that algebra. Not going to satisfy this algebra. Of course, I changed the equation. Of course, it's not going to work. But let's talk about why it didn't work. The 3, the 4, the 12 that make this equation work over here, well, the 3 is supposed to get squared, the 4 gets squared, the 12 gets squared. That's why this algebra works. When I tried to do the same thing over here, the 3 got squared, the 4 got squared, the 12 got multiplied by 2 and became 24. And that's what got squared. That's why it didn't work. I fiddled with the arithmetic. right? I mean, silly observation. Of course it didn't work. But what you can do is you can see what the problem is, and therefore you can see how to kind of mess it up to make it sort of work. And that is, what if I looked at this point here instead, where I look at a 6, where the 12 had been? Right? And keep in mind, the arithmetic that works is 3 squared plus 4 squared plus 12 squared is 13 squared. So trying to plug in this point, 3 squared plus 4 squared plus, okay, wait a minute, 6 times 2 is 12 that gets squared again. So this point doesn't work, but this point does. And this, I'm going to say, always works in the sense that whenever you do this algebraic shift, whenever you replace z with 2z, effectively, in terms of points that satisfy the equation, effectively, all the z coordinates just need to be half as big as they used to be. And making the z coordinates half as big will perfectly balance with this extraneous 2 that I tossed in there, and the arithmetic will be exactly the same. So the nice punchline then, this is the geometric effect. If you replace every z with 2z, your surface just gets squished by a factor of 2 in the z direction. Everybody on board? I'm going to say it a little bit differently. I'm going to say whatever you do to the equation in this sense here, very specific sense, whatever you do to the equation, I introduced an extra factor of 2 in the equation. The opposite is going to happen to your solutions, right? I have to take out a factor of 2 in the solutions that work. So this is a good general rule of thumb, and I'm a big fan of using these ideas to understand surfaces. So here's an example. Let's look at this equation right here. How am I going to understand that equation without the deformation trick? I don't know. It's not rotationally symmetric. I do see an x being squared. I do see a y being squared. I do see that they are being added to each other, but they have different coefficients. And so there's extra x's and extra y's in here. This does not satisfy the rotational symmetry requirement. So I'm kind of dead in the water without this deformation trick. So what I'm going to do is observe that I can fiddle with the equation algebraically compared to something I already understand. This, I already understand that. That's the unit sphere, no problem. Spherical coordinates arguments, easy argument on the left there. And then I notice that all I have to do to turn the orange question I understand into the green question that I don't is these little algebraic replacements. Everywhere there was an x, I replace it with x over a. And I know what that does geometrically. That shifts, that stretches, I should say, outward in the x direction. Doing the opposite of what I did to the equation. In some sense, I divided by a in the equation, and so all the points that are solutions are going to have their x coordinates multiplied by a. So stretching outward in the x direction. Is everybody with me so far? Analogously, by the way, for y, right? So y is being replaced by y over b, and so that's going to stretch by a factor of b in the y direction. So this is a great way to take knowledge that you have of simpler questions and use that as a foot in the door to help you understand a harder question. Right? So now I know exactly what it is that this nastier algebra over here, I know exactly what this represents. This is whatever it is that you get when you take a sphere and stretch appropriately into 3 different directions by these factors that you can see, A, B, and C right there. So what happens geometrically when you stretch out a sphere? Well, you get a what's called an ellipsoid, like so. Everybody good? Really useful trick. I do want to warn you of one little algebraic pitfall here. It's real easy to mess this up. If you have x squared blah 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 on the left, and the question comes up of what do you have to do to get that to look like, let's say I were to have it be x squared over 4 plus blah 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 blah. Right? So what is the substitution that happens here? A lot of students get this wrong. A lot of students see typographically this x over 4 right there. And a lot of students see this x over 4 and like, oh, okay, I guess I replaced x with x over 4. But no. Right? That's not how. It's not about the layout on the page and the typography. What it's about is, let's see here. I need to slide that over. Let me point out this is the same as x over 2 quantity squared. Right? And when I say I'm going to replace x with something, what I mean is everything that happened to x needs to happen now to whatever it is that I replace x with. And if I'm replacing x with x over 2, that, and keeping in mind that what had been x is being squared, that means that what I replace it with, the whole thing, is squared. That's what makes this 4 show up. Everybody see that? Easy mistake to make to think the stretching factor is 4 here, and it's not. It's 2. Everybody good? Okay. All right. Okay, couple more examples here. These are nice little quickies. We already understand a paraboloid. So what's going on with this thing right here? Oh, golly. I mean, we enjoyed a lovely rotation argument with that first one. With this one here, I can't use a rotation argument here. The numbers A and B are presumably not the same. What are the odds? And so this doesn't satisfy the rule. This is not rotationally symmetric. But this is pretty clearly just a stretched out version of the paraboloid. And so since a paraboloid has circular cross sections, when you stretch it out, those circular cross sections become ellipses. Thus we call this an elliptical paraboloid. Everybody good? Okay. Likewise down here, whoopsie, that's a hyperboloid. Previously noted, right? Previously worked on. And, this is different. Not immediately clear. No rotational symmetry argument that we can make here. But what's convenient is I can see, look, there are easy substitutions that I can do to turn dark blue into purple. Right? I replace x with x over a, y with y over b, z with z over c. That just gives me, that indicates how to stretch out my previous hyperboloid, and thus this is called an elliptical hyperboloid. Does that make sense to everybody? There's various other examples in the book. I encourage you to take a look. And I'm going to move along now to section 2.3, talking about derivatives. So we're going to finally do our first calculus. What are we, 3 weeks into the semester? We're finally doing some calculus. Okay, so derivatives. Here's the first little bit of weird news. There are multiple kinds of derivatives in multivariable calculus. So that convenience from single variable, that you can talk about the derivative. Yeah, there's kind of a bunch of different ones in multivariable calculus. Now, I am I've already exposed myself as someone who believes that when you have different ideas, you shouldn't use the same word to describe different ideas, right? My whole thing with orthogonal and perpendicular really bugs me, right? So here it is. We're using the same word, derivative, apparently to describe different kinds of derivatives. So why are we using the same word? We are going to give them different names. We're going to have different little modifiers on there. So the reason that we use a single word to connect them is because they all have something in common. All of the derivatives we're going to talk about in this course, in some way or another, they all relate input changes to output changes. And we'll see this as we go through the rest of this chapter and how we use derivatives in later settings. There's some sort of a relationship, different in every context, different for every different kind of derivative. But there's always a relationship between input changes and output changes. So be on the lookout for that as we go through. Okay, I'm going to start with something called partial derivatives. If you've taken a high school multivariable calculus course, you may have presumably have seen partial derivatives previously. That's okay. That's fine. If you haven't, also okay. Possibly better. We'll see. But anyway, so why I want to emphasize why it is that I'm starting with partial derivatives. There are several good reasons. They are easy to compute, and that's awesome, and that is comforting and satisfying. They're also really easy to relate to single variable calculus. And again, there's that familiarity and satisfaction and the safety of the familiar. And that's nice. There's no doubt about that's nice. Frankly, the big one is the fact that the book does it this way. But for whatever it's worth, if it were up to me, or said differently, in my multivariable calculus book, I don't start with partial derivatives. Because even with all of these advantages, these are really not the best way to think about derivatives. And there's kind of an implicit subtext when you present ideas that the first idea is the most important one, that it's the most fundamental of the various ideas that are going to all connect. You start with the fundamental. And I'm making you call it a hot take if you want, but I don't think partial derivatives are the fundamentally most natural, best way to think about multivariable derivatives. I think they're a convenient algebraic tool, and ultimately not where you should hang your hat. Your basic intuition. When you leave this course, when someone says multivariable derivative, I do not want you to think partial derivatives. The thing that I want you to think of is something we're going to build up to later. So why do I start with something that I wish I didn't have to start with? And again, well, it's because the book does, and I kind of feel like I sort of have to. Okay. All right. Okay, so let's do it. Let's actually talk about some partial derivatives. Here's the rule. If you have a multivariable function, lots of input variables, pick one of the variables. Just one. Hold all of the other variables constant. Don't allow any of the other variables to change. Just momentarily, just while we're computing a partial derivative, hold all the other variables constant. And if you think about it, if you have a bunch of variables, but most of them are constant for the purposes of our argument, what results is actually a single variable function. Right? So this idea of fixing all the variables except for one turns a multivariable function in effect into a single variable function, and then we just take the good old regular plain old derivative, single variable derivative of that single variable function. So this is how we compute partial derivatives. Now, before I get into the little notation and stuff, I want to address what I hope you may be concerned about right now, which is this seems awfully arbitrary. Wait, hold all variables constant? When does that happen in real life, that only one thing changes at a time? That's not how the world works, right? That's part of my quibble with why I think this is an unnatural point of view on derivatives. So granted, right, you should be suspicious as to whether this is actually a good idea. You should be suspicious. Does this have any natural geometric interpretation? I've made this seemingly unfair, random almost choice to just take a bunch of variables and pretend like they're not variables. You should be very highly concerned or very suspicious. And I'll address all of that a little bit later. So all of that said, what do we interpret from what do we interpret from this notation? How do we interpret partial derivatives? Here's how we write them down. Various different notational options. This is kind of the easiest one to start with. It looks pretty familiar, right? It kind of looks like dy dx, roughly. Not exactly, but roughly. Whichever variable is the one that you have left as a variable, that's the one that you put in the denominator. After all, that is the variable that you're taking the derivative with respect to. That's pretty believable notation, I think. The next one is just a twist on that. This is kind of just morally equivalent. We've seen analogous things in single variable calculus. And there's this one here as well. This is arguably a little weird. Whichever one is your variable, you make that a subscript. Very handy in some circumstances, and we'll see some of those circumstances here and there. But anyway, either is fine. Okay, now please do be very careful to notice that this symbol right there, right, that is not a lowercase d. Very important. You cannot put a d there. That's wrong. That's not notational preference. That's wrong. Okay, so now a lot of students, okay, hey, noted, I won't do that. But then they think, okay, so then they're going to use this. Whoopsie, I missed the thing. They're going to use the lowercase Greek letter delta. Also wrong. That's totally different character. So this symbol here that we use to represent partial derivatives, that's just a brand new symbol. If you haven't rehearsed how to draw that symbol, then it's going to seem a little unnatural the first couple times. It almost looks like kind of a backwards 6, maybe, kind of, right? For whatever it's worth, I think it's however silly it may seem, I think it's worth your time to spend about 2 or 3 minutes with a sheet of paper and a pen and just kind of decide how are you going to make this new symbol, right? And you got to make sure that it doesn't end up looking like a D and that it doesn't end up looking like a 0, right? And it doesn't end up looking like any of several other things that, if you're not careful, that it might end up accidentally looking like. Okay. So a real quick example. Let's see, how much time do we have? Yeah, I got a minute here. This example I'm going to show you is actually really quick. How would I take this partial derivative right here? Notice partial with respect to y. Y is my variable. That means I'm doing this as a function of y. That means everything except for y is to be treated as a constant. That means that x is a constant. That means e to the x is a constant. That means that z is constant. That means all of this is constant. And basically what I have here is a great big constant times y squared. How do you take the how do you take the derivative of the single variable function constant times y squared with respect to y? That's no problem. That y derivative is just 2y. And the multiplicative constant just sticks around for the ride, as multiplicative constants do. So, super easy to take that partial derivative. Y'all have a good day. See you later.
Thank you.